Hey everybody, this is Dr. Lejo Flores, and today is a short video lecture for hydrologic modeling, and the topic is going to be model forcings. This is a really important topic when it comes to hydrologic modeling. It's also one for which there aren't really sort of good off-the-shelf resources to facilitate this discussion, and this is actually one of the areas that there's often kind of the most confusion amongst new modelers, and there's just a lot of uncertainty on what is kind of the best way forward to find and use forcings for a hydrologic model. So we'll start off with the learning outcomes for this video lecture, and they are as follows. So by the end of this presentation, you should be able to distinguish between the different terminology that we use when it comes to forcings, and you'll understand that there are a lot of different terms that people use, most of them interchangeably, and that's often, again, sort of a source of confusion for new modelers. You should be able to list the key environmental variables most commonly required as forcing products, and those will often depend on the model that you're actually using. You should be able to explain some trade-offs between alternative forcing products to be able to sort of balance what the capabilities in terms of the forcing data are versus what the capabilities and needs of your model and your application are. And then finally, you should be able to appraise the appropriateness of different forcing products for a specific application. So based on this lecture, if I were to give you an idea of, here's a use case that you might encounter as a modeler in the future, either as a researcher or as a practitioner, how would you go about finding what an appropriate forcing data product is for that application? So first off, I want to cover this idea of what do we actually mean when we say forcing. That's sort of a weird word. One frustration I have as a modeler is that when I'm writing either journal articles, emails, reviews, whatever, the various word processing software, whether it's Word or Google Docs, wants to always correct this variable because we're not using it in sort of a canonical term. So in the context of hydrologic modeling, when we say the word forcing, typically we are simply referring to the meteorological inputs to our model, right? So the various variables that characterize the surface meteorological environment that will affect the land surface water and energy balance in ways that our models need to account for, right? So but forcing is sort of a loosely used word in part because there's not a formal definition for it, and so sometimes you'll hear a variety of different terms and words used pretty much interchangeably, and that again can be the source of confusion. So some of those other terms that people will use include things like hydrometeorological forcing. So we're just modifying the word forcings by the term hydrometeorological to make sure that people understand that we mean those surface meteorological variables that affect land surface water and energy balance. Some people might say the environmental forcings. Some people might say environmental inputs to the model. Some people might just say the metadata, right? And so all of these terms get used synonymously or interchangeably by various people in the field, and that sometimes can be sort of the source of confusion or uncertainty when you're just sort of starting out. But generally speaking, all of these terms are interchangeable for one another, and what we mean are just those variables, again, that drive the surface water and energy balance. And so what are those variables? Okay, so this is a schematic diagram of a land surface model, the so-called NOAA multiphysics or NOAA MP land surface model. I obtained this from the NOAA MP website at the Jackson School of Geosciences at the University of Texas. And this provides a schematic representation of what NOAA-MP is simulating or modeling, right? So it, as the name implies, is simulating the land surface water and energy balance, right? So it's simulating things like the accumulation and ablation of a snowpack, the infiltration of water into the soil, and its percolation through the soil, its recharge to an unconfined aquifer layer, as well as the uptake of that water by, for instance, roots of trees or grasses, the evaporation of water that's kind of ponded from the surface or just on the surface of plants, the so-called wet evaporation or the canopy water evaporation. So in essence, NOAA-MP and other land models and other hydrologic models like it are simulating, some combination of these different land surface water and energy fluxes and stores. And in order to do that, they need to be supplied with forcing products. And so what are the key forcings that we have? Well, we can think of these in sort of two different buckets, right? So we need to know kind of the amount of water that is being supplied by the atmosphere. So that is just simply the precipitation, right? So or also potentially the condensation. So we need to know how much water is basically coming out of the atmosphere and arriving on the land surface, right? So we think of that, the vast majority of that as being precipitation. So what is falling into the landscape that our model then has to redistribute, right? And correspondingly, from the other direction, what is the demand of the atmosphere for water, right? So how much water is the atmosphere demanding to drive from the land surface through processes like transpiration and evaporation or evapotranspiration collectively. Now, it's pretty clear that the precipitation term, so what's coming in, is just that sort of precipitation. We need to know what the flux of water from the atmosphere to the land surface is, right? The flux the other way, the ET flux, the evapotranspiration flux, is a bit more complicated, right? So it certainly depends on what the atmosphere's demand for water is, but it also depends on how much water is in the land surface. It depends on sort of what kind of vegetation you have, what kind of soils you have, whether that vegetation is sort of happy and unstressed, things like the color of the soil, and things like that, things that sort of serve to constrain or withhold water from the land surface moving back to the atmosphere. So as you might imagine, there's a complex set of additional sort of forcing variables, surface meteorological variables that determine that demand of the atmosphere for water, as well as the extent to which the land surface is able to provide or meet that demand, right? So that includes things like the air temperature, right, and the humidity, which together we can get an estimate of the so-called vapor pressure deficit, right? So how much more water the atmosphere can hold. We need to know things like the wind speed. So the wind speed will sort of help us determine the extent to which evaporated water can actually be translated or moved away from the surface. So we need something like a wind speed at or near the surface. We also need to know the incoming energy that's available to drive processes like photosynthesis that causes plants to lose water in the course of gaining carbon dioxide for the process of photosynthesis, right? So we need to know how much radiation is coming in, both from the sun as well as potentially long wave radiation that's radiated from things like clouds and or nearby vegetation or nearby landforms. So by and large, the variables that we often most associated with this kind of bucket term forcing are things like 1, precipitation, 2, air temperature, 3, some measure of humidity. That can be relative humidity, or it can be the dew point temperature. 4, the wind speed and potentially the wind direction. 5, some measure of radiation, right? And so frequently we think of that as the incoming or the downwelling or the downward flux of solar radiation or shortwave radiation and long wave radiation, because both of those are available energy to drive evaporation from the surface. So those are the terms that we are most often in need of when we are running a hydrologic model. So what are the sources of forcing data? I could create a more than semester-long, probably even a year-long class just talking about where we get forcing data from. This is a very sort of complicated and very fraught discussion. And the idea is that it's exceptionally important because we're often in the need of high quality, accurate forcing data for our models at spatial and temporal resolutions that are appropriate to the model that we're using, and that sort of meet any other needs that we might have as modelers. And there are many different sources. If you did an inventory of all of those different forcing data products, if we were to sort of draw up, spend a whole day, putting sticky notes up on a whiteboard and listing all of the different potential forcing products that we have, we could largely bin those different forcing products into effectively sort of 3 different groups or 3 different classes, right? So if you did that, you would find that one of those kinds of buckets of forcing products corresponds to the output from other models, right? And we'll talk about what those models are and why we would use them. The second bucket is actual observational data, right? So we have a weather station or we have some other form of observational data, and that's what allows us to characterize the surface environmental forcings where we care about them. The third bucket, or the third sort of grouping of meteorological forcings, corresponds largely to sort of a hybridization of that model output and data, right? So there are pluses and minuses to all of these, and so oftentimes what hybrid methods seek to do is sort of combine models with observational data to get sort of a merged product that sort of gets at the strengths of each of those 2 subgroups, model output and observational data, and uses the strengths of each of those groups to sort of compensate for the weaknesses of the others. So what we're going to do is, in the next few slides, we're going to go through each of these 3 different groups of forcing data products, and I'm going to give you sort of a specific example of each of them. Again, this is not an exhaustive list by any stretch of the imagination. There are probably literally hundreds of different forcing products we could talk about. But I'll provide you with a brief specific example, and then we'll go through and we'll describe really kind of the pros and cons, or maybe better yet, the sort of strengths and weaknesses of using each of these. So let's talk about using model output as forcing first, right? And so the specific case I have here, the specific sort of what this looks like basically is here we're when we talk about models, right? So we're talking this class is about hydrologic modeling, and now we're talking about using output from other models as input to our hydrologic model. And so it's important to understand that this is, that there's a distinction here. And the model output that we're using as input to our hydrologic model will most often correspond to output from something like a numerical weather prediction or NWP model, or an Earth system model, or what in previous times was commonly referred to as a climate model or a GCM, right? And so you might think about why you would use each of, what are sort of some specific applications for which you would use each of these products, right? And so there are many of these different NWP model outputs, Earth system model outputs that you could use to drive a hydrologic model. On the bottom here we have an example of one specific variety of that. This is the so-called high resolution rapid refresh, or HRRR model. It is a forecast model, so what you're looking at is an 18-hour total accumulated precipitation forecast in inches for the continental United States, right? So here's Boise right here. Here's Billings, Montana. I think that's probably Sacramento. This is the accumulated precip, what this numerical weather prediction model thinks the total precipitation will be if we started from 1500 universal coordinated time on October 29th and went forward 18 hours, right? And so the total here is in inches, and so it actually right now happens to sort of be snowing in Colorado, so this is forecasting somewhere in the neighborhood of a quarter of an inch to maybe an inch of snow in the Colorado Rockies. It also looks like maybe there's a kind of a weak low pressure system in the southeast, where we might actually be getting some pretty heavy precipitation over this 18-hour period, maybe between 5 and 10 inches of precipitation off the coast of Florida and Alabama here. So, so the nice part about this is that, this is a forecast product. I went and downloaded this image. I could go and actually get the underlying data that was associated with creating this image, and I could take it. I could write some Python or R scripts to take that data and transform it into the format that my hydrologic model wanted as input, right? So that's a nice attribute of this data set, right? It's associated with about a 3-kilometer spatial resolution, and like I said, it's based on a research grade weather model called the Weather Research and Forecasting, or WRF model, and the data is made freely and openly available to anybody who has an internet connection. So clearly, there's some benefits to using model output as forcing for our hydrologic model, right? So as you just saw on the previous slide, because it's model output, we know that there won't be any spatial or temporal gaps during our period of record, right? If there were, the model, that numerical weather prediction or climate model would not have run, right? It would have sort of crashed. And so we can be confident that when it comes to using that output as input to our hydrologic model, when we need a precipitation value at a particular space and time, it will be there. Another attribute is that it is, because it comes from a model, it will be internally consistent. And what do I mean by internally consistent, and why is that important? By internally consistent, we mean that it is that data will be consistent with the physics that are in that numerical weather prediction model, right? So we would not expect, and we would not find, for instance, a really heavy precipitation rate at a location where simultaneously the solar radiation is really high, right? So we're not going to get really heavy rainfall while the sun is shining, right? So that's sort of a nice attribute. and something that's really important in terms of the hydrology model, right? Because if we supplied inconsistent forcing to our hydrologic model, we'd likely get inconsistent results. Similarly, what's nice about using model output is that it often, because again, it comes from a model, is going to come in a uniform data format that we can sort of always be prepared to use, right? So the idea here is that we download our data. That data sort of comes packaged as maybe a variety of different files of a particular format. And what we need to do is just create sort of a translator script using some high-level programming language like R or Python, and maybe some software packages that support that, to take that data, read it from its native format, write it to some other format that is needed by our hydrologic model, and then save it, right? And so that's a pretty straightforward and easy step, right? There's not much, no fuss, no muss when it comes to that workflow process. And once that sort of translator script is written, you can be sure that if you want to apply that hydrologic model to a different period of time, all you have to do is go and get the associated forcing data and just rerun that same script, for that different period of time. Alternatively, if you wanted to sort of set up your model and run it somewhere else, you would just presumably reuse that translator script, supply it with sort of a different location to kind of cut out your forcing data, but largely the workflow would be exactly the same. So there are some associated drawbacks with using model output as input to a hydrologic model. The first and foremost, obviously, we are we're using a modeled product, right? So that upstream model, that numerical weather prediction model, that climate model, it has some uncertainties in it. It is not a perfect representation of the physics of the atmosphere or the climate system. And so it's going to get, just as your weather forecast can be wrong, it's going to have uncertainties associated with it, right? So sometimes it's going to have precipitation where none actually occurred, or it won't have precipitation where precipitation actually occurred. And that's problematic when it comes to then using your hydrologic model output and comparing that to observations, right? Because, for instance, if you're comparing stream flow and there's an observed peak in stream flow from your gauge observation, but your model doesn't show that, is there something wrong with the hydrologic model? Or is it just that precipitation event that caused the observed peak in stream flow just didn't show up in the data that you used as input to the hydrologic model, right? So clearly there are some issues that we have to sort of think about and cope with when it comes to using the output of something like a numerical weather prediction model as input to a hydrologic model. Another thing that becomes an issue, particularly for those of you and us that are interested in modeling things like an individual watershed, right? A small watershed that may be tens or maybe hundreds of kilometers in spatial extent, but at sort of higher resolution. The spatial resolution of many of these products, particularly those that are produced by national or global forecasting agencies or organizations, they're having to provide a global or continental scale product, and because they have limitations on the size of computers they can use, they have to not do everything at really high spatial resolutions. And so when you talk to folks in the numerical weather forecasting and numerical weather modeling business, high resolution for them might be something like 4 to 6 kilometers. But if you're interested in an individual watershed, say Dry Creek Experimental Watershed out here, all of Dry Creek is contained in a single pixel, in a single 6 kilometer pixel. And so the question is how really representative of the spatial and temporal variability of the meteorological conditions in Dry Creek is that single pixel? The answer is probably not that representative, right? It probably represents either a high or a low or maybe something in the middle, but it doesn't represent the fact that we often get only snow up high in the watershed and only rain down low, and that the mean annual precipitation varies from something like 300 millimeters at the bottom to 1,000 millimeters at the top of the watershed, right? So we don't have sufficient spatial resolution from some of those forcing products for our specific applications. Another thing that can occur, which is more subtle but kind of equally important, is that because those forecasting organizations and agencies are continually trying to update and improve their forecasts, which is good, they will sort of have sort of very discrete periods in time where they will update the model, right? So they'll use a new version of a model. They'll use a new version of their grid where they're simulating. They'll maybe use new satellite observations to kind of create the initial conditions for their models, and they'll just sort of keep running those models forward. And so for those of us that are sort of end users of the output of those models, we need to be a little bit careful in thinking about, well, what do we do when when the National Centers for Environmental Prediction updates their global forecasting model? What do we do when some forecasting organization uses a completely new grid? That will definitely sort of have an effect on our simulations, our hydrologic model runs, but it's often not clear how. And so one thing to think about would be, how would you go about trying to assess the impact of that model improvement on the prediction that your hydrologic model gave? So the next kind of broad bucket of forcing data that we'll talk about is actual observational data, right? So this is data that comes from sort of surface, meteorological and other stations that we can use to provide input to our hydrologic models. And so some very specific use cases that I have here, sort of near and dear to those of us in Idaho, is the NRCS, the Natural Resources Conservation Service of the U.S. Department of Agriculture, the so-called SNOWTEL data network. Another is the National Climate Data Center, right, which is sort of a clearinghouse for a variety of surface meteorological observations throughout, in particular, the continental United States, right? So both the NRCS SNOWTEL data and the NCDC data, the data that you frequently get from NCDC, this is most often sort of point scale observations at an individual weather station, right? We could sort of contrast that against something like the NEXRAD, the National Weather Service's NEXRAD, in particular the level 3 radar data, which obviously would be sort of precipitation only for us, but because its radar provides kind of a spatial, spatially filled precipitation observation from the radar. So as a specific case, what I've provided here is just a screenshot of the SNOWTEL observations here in the Central Rockies of Idaho. Boise is right here. The nearest SNOWTEL station to us is up at the ski area Bogus Basin, right? And so as you can see, these are the observations or the locations of the SNOWTEL observing network throughout kind of our neck of the woods. This is basically kind of the majority of the Snake River Basin. So one thing to do when you look at this, and I've provided the website where you can actually go and use this interactive map to see where the observations are and actually use it as a portal to access the data. Some questions that you might have, or some reflection you might want to do as you look at a map like this, is to note where the observations, where the SNOTEL stations are, and where are they not, right? So that would be a good sort of, quiz exercise or reflection to ask you to do. And then another question that's sort of maybe a level up from that question is to think about or do some digging on, what is the purpose of this SNOTEL network? Why was it initially created? What are the agencies that are funding it, that are keeping it going? And so what is the principal aim and use of that data? And if the answer is not, and I can confirm that the answer is not, if the answer is not for use in hydrologic models, then what are the implications for using that data as input to a hydrologic model, right? So that's just some food for thought for you as we continue talking about forcing data. So the benefits of using observational data as input to our model are that it's obviously observational data, right? So it was data collected typically through an automated sensor platform, but it was an actual observation of the specific location where that station exists, right? And because we know that instrumentation, and we know the kind of instruments that are on those platforms, it's not as if those observations are error-free, but we do know a bit more about the errors in those observations, right? We can go to the manufacturer of the sensor and ask of them what the precision is, or what the sort of typical error of that observation is. So we have a little bit better constraint on what the errors in those observations are. Now, there are some key drawbacks to using observational data as input to our hydrologic models. Principal among them is that some of these observations, and in fact, when you actually think about it, almost all observations are actually retrieved from observations of something else, right? So most clearly, we can think of that in terms of things like precipitation radar, weather radar, NEXRAD, right? So what is actually, we're getting a number that is a precipitation, but where did that come from? Well, it turns out that the radar itself was measuring the backscatter of a microwave beam that got sent out from that weather radar dome, and there was a retrieval or a conversion of what the actual radar observed, right? So something from reflectivity to precipitation, right? And so one sort of one thought exercise is, well, how did that relationship between precipitation and what the sensor actually observed come into being? What does that relationship look like? And are there uncertainties associated with that retrieval from what's actually observed to what we actually want to input to the model? So that's a really good exercise to think about. But if you extend that thinking, it's actually true that most sensors that we have, even of sort of surface weather observations, are not direct measures of the things that we actually care about, right? So if you think about precipitation, and for instance, if you've taken Jim McNamara or somebody else's hydrology class, they talk about different types of rain gauges, right? And so what's actually being measured, for instance, by a tipping bucket rain gauge is not really the precipitation depth, but it's kind of the number of times that little bucket inside the funnel sort of tips, right? And so in principle, it required a certain amount of precipitation for that bucket to tip, but there are other things that can cause that bucket to tip or not, right? Conversely, there's also weighing bucket precipitation gauges, right? So you're actually weighing the additional amount of fluid, of liquid that comes in as precipitation, and assuming that all of it comes in as precipitation, right? So it's true as well that many of our observations of those variables are actually, there is some degree of uncertainty associated with them because, we're not actually measuring the variable that we actually care about. Another drawback is that, because we can only put weather stations out at individual sites, we have to ask ourselves, well, how representative of the broader landscape that I'm trying to model is that individual weather station representative of, right? So is it truly kind of capturing kind of the mean behavior? Is it just kind of it's a quirky location for where that weather station happens to be, and it's not that representative? And how would you ever know, right? Particularly as you're trying to sort of model potentially watersheds that are large, in which you'll never really be able to get out to all of the weather stations, or you're using data from a weather station location that doesn't exist anymore. That's not at all uncommon, right? So you have to think about the degree to which that individual point or small volume of the atmosphere that surface weather observation is characterizing, the degree to which it's really representative of the larger landscape that you're trying to simulate. And often it's the case as well that there are just a variety of different gaps in the data that is observed from surface observations, right? So data loggers go down, sensors fail, sensor networks need to be replaced, batteries fail too early, solar panels get covered with dust, and so it's not at all uncommon to have gaps in the temporal data record where we need forcing, right? And so the question is what do you do when you have those gaps? That's a whole topic unto itself. And then finally, we went through the most common variables that need to be measured in order to force many hydrologic models. And it's also the case that not all observational networks or observational sites will characterize or measure all of those variables that we need, right? So you might have a site at which you just have precipitation, temperature, and wind speed, but not radiation, right? And so the question is what do you do under those circumstances, right? How do you augment the data that's actually observed with other data such that you have an entire kind of set of data to force your model? So recognizing the benefits and strengths of and weaknesses of those two methods, or two kind of groupings of forcing data types, be they model output or observational data. One might ask, well, why not sort of try to have the best of both worlds and combine observational data and model output to create those model forcings? And the answer is that that's a very common thing, right? And so two specific cases that I would refer to here are the so-called PRISM data, or the parameter regressions on independent slopes model, right? So it's a very commonly used, widely used surface meteorological and climate data set developed at and hosted by Oregon State University. And it's a geostatistical model that interpolates surface weather and climate observations. Another set of hybridized forcing data is the so-called NCEP, the National Centers for Environmental Prediction North American Regional Reanalysis, or NAR data. And what I have for you here is a quick output plot from the NAR data that I just did this morning on their website. So NCEP NAR data has this is what you're looking at here is the global averaged precipitation from October 1st of this year to October 15th, so the first half of the month of October. And so the NCEP reanalysis data It uses model output, but it constrains it or combines it with a variety of surface observations as well as satellite observations. So things like atmospheric temperatures, surface temperatures, sea surface temperatures. So it uses a variety of sort of complex algorithms to kind of combine all of that to get what we think of as maybe being a best guess of what the actual precipitation was over the globe at this spatial and temporal resolution, given the data and models that we have. So the NCEP, the NAR data is available from about 1979 on January 1st onward. It's a data product that gets continuously added to. It's global in coverage, and so it has a coarser spatial resolution of 32 kilometers, but it has a 3-hour temporal resolution. And I've provided the website here where you can actually find more documentation about the NAR data as well as download the actual data. So what are the benefits of using a hybrid product? Well, again, it's spatio-temporally consistent, right? So it often is output of some physically based or some geostatistical model, and so it's going to have a estimate of key variables like precipitation and temperature at every grid cell and at every time that we're interested in. And because in particular in the case of things like the NAR data, it comes from something like a climate or global weather model, that data will be internally consistent. So again, we don't or have less of an issue of having sort of, for instance, a really high precipitation rate with a really high solar radiation, right? Because we are ingesting observational data, we tend to reduce biases in the underlying model estimates, and we might sort of correct some other error structures that exist within that model because we're ingesting those observations. Because we are sort of hybridizing our observations and models, we have a little bit more control and some potential improvements in the resolutions, right? So, and the two products that I just referred to on the previous slide, PRISM has a spatial resolution of 4 kilometers for free, or 800 meters if you're willing to pay for it. It's daily data, whereas the NCEP NAR data, although it's coarse in spatial resolution, right? So it is 32 kilometers spatial resolution globally. It's much higher in temporal resolution. So we have 3 hourly 3 hourly estimates of those surface environmental forcings. But that sort of leads me to the first drawback, which is that often we have to sort of trade off that spatial for temporal resolution, right? So something like PRISM is higher in spatial resolution and is maybe appropriate for many of our hydrologic applications, but it's only daily data, right? So you get a daily total precipitation, a minimum temperature, a maximum temperature, and you don't have that sort of diurnal signal that some models might require. Conversely, the NAR data is obviously for many applications in mountain watersheds, it's far too coarse in spatial resolution to take out of the box and use as input to a hydrologic model, although it does have a better temporal resolution. Other sort of questions that you would want to ask yourself when you are using or finding a hybrid forcing product is, well, what are the details of how those observations and models were combined? What are the details of the model that was used to sort of distribute my observations or create or predict the precipitation and then and other sort of environmental surface variables? But also how did we actually go about combining those observations with the model data, right? What were the specific algorithms? What are the assumptions that went into those algorithms? What are the assumptions made about the data that was used to ingest the models into the models? And then again, sort of echoing to using model output as input to a hydrologic model, what happens when there's either new models updates to the underlying model, or when new observations become available, right? On some level, that represents kind of a discontinuity. Maybe we're getting better data products, better estimates, more accurate estimates of those surface forcing variables that we need as input to our models, but it's also not immediately apparent how we should treat those circumstances when there was a big change or update to the model, or when new observations get ingested into that model. And so again, often we may not be doing anything about those last two bullet points, but I think that they merit more thought than sometimes we pay to them, right? So those are definitely questions we should ask ourselves as we go about sort of trying to find or use hybrid forcing products. Okay, so based on that, I guess that you might be sort of asking yourself, well, how do I choose a forcing product? We've provided sort of strengths and weaknesses for each of those sort of three groupings or buckets that we just covered, and it's still not immediately apparent, that there is a correct answer or a correct product that is sort of universally appropriate for all applications, and that's correct. It's almost true that it's almost always true that that the correct forcing product is going to be a function of the specific scientific, engineering, or management application that you're undertaking, right? Or the location and time period that you're interested in modeling, right? And so because of that, it's always important when you undertake any modeling project to kind of ask yourselves to do this kind of rundown of asking yourself these sort of few questions down here to determine what the best pathway is for finding and or using forcing data products, right? So so ask yourself, what's the application that I'm undertaking? What's the underlying science or engineering question we're seeking to answer? How precisely do I need to know that answer, right? Is it a matter of life and death for me to get the discharge correct, or is this more of sort of a scientific application where as long as the errors are sort of consistent with one another, I can live with a little bit of error? Additionally, what kind of hydrologic model is being run? Are you running a very sophisticated, spatially distributed, physically based model, or are you running a more simple, lumped parameter conceptual model, right? So the answer to that question will have a large, impact on what forcing product you ultimately will choose in your application. Because you may not need as detailed of hydrologic or hydrometeorological forcings as you think you need, because you're running a simpler model, right? Or conversely, you might be running a model where it's exceptionally important to get decent or good hydrometeorological forcings for your model. And then finally, obviously, sort of what products are even available, right? So if you're doing some applications, for instance, in sub-Saharan Africa, for instance, the products that will be available are a much smaller subset of those products that would be available, for instance, somewhere in the continental United States, right? Even in the continental United States, there are data gaps, right? So we have issues of observational coverage here in the central mountains of Central Rocky Mountains in Idaho, in ways that you don't necessarily have in, for instance, the Southeast or in the Midwest, right? So it's also just a product of, well, what is there to actually use? So that sort of wraps up our introduction or discussion of alternative forcing products. But along the lines of those last kind of determinants of how you might use, I've posted these kind of reflection questions that I'd like you to spend some time thinking about, right? So here I've provided sort of 4 different potential use cases. These aren't sort of specific to any particular project, but they are ones that you could imagine being sort of legitimate scientific or management questions that need answers to, right? So read through each of these prompts below, each of these kind of use cases, and maybe use those 4 questions on the previous slide, right? So what is the application? What is the availability of data? How precisely do I need to know the answer? And what kind of model might I be using? Use each of those sort of against each of these potential use cases, right? And think how these use cases are different from one another, and how what's being asked ultimately might determine what kind of forcing data you might use, right? So the first one is, let's say you're conducting an assessment of future climate change, of how future climate change might impact summer stream flows in the Columbia River, say for fish purposes. Fish habitat. The second might be, you are you're working for an organization or an agency that is tasked with providing a forecast of river flows in the Boise River during the next 120 hours, right? So let's say that that's either for flooding purposes or maybe for water supply purposes, but so 120 hours is 5 days out. You need to sort of provide a forecast of what the river is going to do over the next 120 hours, and maybe you need to do that sort of once a day, right? So how would that impact the choice of forcing data? A third might be if you are tasked with assessing how the hydrology responded in the South Fork of the Boise River after the Elk Complex fire in 2012, right? So this was a large fire, burned a good chunk of the South Fork of the Boise River, resulted in a lot of mudslides and landslides, debris flows in the South Fork of the Boise River, impacted some water quality issues in the Anderson Ranch Reservoir area. If you were if you were asked, hey, how much more water did we get, or what was the timing of the stream flow after the Elk Complex fire, how would you go about trying to determine what the appropriate forcing data product is? And the final one is a maybe very sort of science-y case, but one that's interesting nevertheless, right? So let's say that for whatever reason you're working in an interdisciplinary team, and you have maybe some paleoclimatologists, and you have some folks that are interested in lake sediment dynamics, and you're the hydrologic modeler. You are asked with producing stream flows for a period in the Holocene, maybe like a monthly stream flow or something, in the sort of the rivers of the Central Rockies here, and that stream flow is being used being used as input to a lake model for Lake Idaho, right? And so this is clearly an application during a period of time in which there were no observations, at least direct observations of things that could be used to drive a hydrologic model. And so, well, what would we do? Where would we turn to get forcing data for our hydrologic model? So, take some time and think about how each of these use cases might affect your choice of forcing data for a hydrologic model, and bring that sort of that discussion or be ready to speak about that in class.